So we don't necessarily need to know all the details if we're not maybe particularly interested in this question, but at the end they say how many BTUs per hour are needed. That's the big thing we want to look for. The units, BTU per hour. And if we look at what we're given, they give us 20 BTUs per hour per square foot. So you could write it like this, 20 BTUs per hour, and then make a big fraction under here per square foot. So foot squared. So this is what we have. We want this in the end. So we need the square feet to go away, and then we'll have BTUs per hour. And that's why they give us 1,500 square feet. So if we multiply this fraction by 1,500 square feet, these units cross cancel because one is in the numerator and one is in the denominator. So since this is already in like the numerator of a fraction, because you could put it over 1 if you want, 20 times 1,500. So it looks like it's 30,000 BTUs. Extra zero there. 30,000 BTUs per hour. This problem gives us a formula to help us calculate the coefficient of performance of a system. And they say Q is the amount of heat produced and W is the amount of work it takes to produce that heat. So this system is 30,000 BTUs per hour of heat, and then it requires 8,500 BTUs per hour of electricity. So what's its coefficient of performance? It's 30,000, that's the amount of heat, that's what they said Q is, divided by 8,500, the energy we have to put into the system. So 30,000 divided by, what was it, 8,500? So we can round this, 3.53 is its coefficient of performance. So we can use that number we calculated in part 2 to compare one heating system to another to see how efficient they are. Energy, the energy you put into a system, the energy you get out of a system, we can compare those two using the coefficient that we just calculated. The higher coefficient means it's more energy efficient. So in part 3, an oil furnace consumes 2.5 gallons of heating oil per hour and produces 175,000 BTUs of heat per hour. And then it says assume 1 gallon of heating oil is 140,000 BTUs. So before we can just plug the numbers into that formula that we just used, remember what we plugged in before were just BTUs per hour. This one gives us gallons of heating oil per hour. So we need to make a little bit of a conversion. So the amount of heat it produces per hour is 175,000. That's what Q is, the amount of heat produced per hour. And then we're going to divide that by W, the amount of work needed to produce that heat. So we can't plug in 2.5 because you'd be dividing BTUs by gallons, right? But what we can do is convert 2.5 gallons into BTUs, because they said 1 gallon is equivalent to 140,000 BTUs. That's the ratio. Or we could say it equivalently that 140,000 BTUs are 1 gallon, right? And so I'm going to use this second fraction, the second way of writing that ratio, because I want to have BTUs. That's the whole goal, is to be dividing BTUs by BTUs. So 140,000 BTUs for 1 gallon. We want to multiply that by the number of gallons we have, 2.5 gallons. That way the gallons units cross cancel and we're left with just BTUs. So we got 140,000 times 2.5, so that's 350,000 BTUs. Okay, so this thing uses 2.5 gallons per hour. We just converted 2.5 gallons using this rough approximation probably for how many BTUs 1 gallon of gas is. That's 350,000 BTUs. And so when we divide those two, that's 0.5 for a coefficient. So this one is more efficient. With the energy that we put into the system, we get a lot more heat out than what we get from this system. So there's a lot of information in this problem, And when that happens, it's often good to just focus on the main goal. The goal is to calculate how many years it will take before the heat pump is saving this homeowner money. Okay, so there's two systems right now that they're considering: electric heating system and this heat pump system. The heat pump system is more efficient. You give the heat pump system 1 BTU of energy, and it converts it into, what does it say, 3.5 BTUs of heat. But if you give the same BTU of energy to the electric system, it only produces 1 BTU of heat. So the heat pump system is pumping out 3.5 times as much heat per unit of energy. Okay. So that's the goal, is to find out how many years it will take. So the easiest way probably to do that, to keep our thoughts straight, is to make two equations, and then we can set those equations equal to each other and solve with algebra. But the first thing we should probably do is, they're measuring things in terms of BTUs and kilowatt hours. We'll need to convert those so that we're talking about the same unit. And we'd also want to calculate how much energy this home needs per year. The first part they say is the square footage of the home and how many BTUs per year they need per square foot. So the energy needed to heat the home for the year is found by taking the 1,800 square feet, and then we want to multiply that by, here, I got to draw this out so we can see the units cancel. Got 1,800 square feet, and if we just multiply that by the 50,000 BTUs per square foot, so per means we make a fraction, here's the square footage, the square feet units cancel, and this will calculate how many BTUs we need per year. So we got 1,800 times 50,000 BTUs, so this home needs 90 million BTUs per year to be heated. Okay, and these are estimates. I think I got this estimate from a local power company. I don't remember where, but 50,000 BTUs per year per square foot. That's an estimate. Depends on the home, depends on insulation, things like that. So this is BTUs per year. Now later on, we're going to have to deal with costs from the electric company, and the electric company has things in terms of kilowatt hours. Okay, so that's a different way of measuring energy. So it would be helpful just to start converting BTUs to kilowatt hours, and so we can use this conversion factor. They tell us 1 kilowatt hour is equal to 3,412 BTUs. So this is 1, right? I'm dividing something by an equivalent amount because I said they're equal to each other. So I'm going to multiply that by 90 million. That way my BTUs cross cancel. BTU cross cancels up here, down there. So you're going to have 90 million over 3,412. So we're going to divide those. So it looks like we're going to need 26,377, I'll just round some decimals here, this many kilowatt hours. That's how many we need to heat the home. Now the first home has a coefficient of performance of 1, so that means things are going to be pretty simple. It means every kilowatt hour you pump into the home, it pumps out an equivalent kilowatt hour of heat. So the cost, we'll call it C1 for the cost of the first plan, is going to be, what do they say? Cost is 16 cents per kilowatt hour. Let's see. So you need this many kilowatt hours. Uh, 16 cents. It's 16 cents per kilowatt hour. Sorry, I should write that on the bottom. 16 cents for 1 kilowatt hour. And then if we multiply that by this kilowatt hour per year, I should write. Okay. 26,377.49. This is kilowatt hours again per year. So we're multiplying those because we're trying to determine a cost. We want just dollars left over. So the kilowatt hours are going to cross cancel in this calculation. But you're still going to have years in the bottom. The years is the variable. We don't know how many years we're going to run this system, so we're going to multiply this by T years. Now, if you check out your units cross-canceling, kilowatt hours, they cross-cancel, years cross-cancel. So we're going to have just dollars, which is what we wanted. That's the cost for this unit. Did they say anything about the startup cost, though? One second. Oh, it says the electric system costs $4,000 to install. So one extra thing I'm going to add over here is the $4,000, and I'm not going to multiply that by T because that's just a one-time thing. It costs $4,000 to install this thing. Okay, now we get everything. So the cost per year plus the startup cost. I'm going to multiply the 0.16 times 26,377. So that's the cost per year for this first system. We're multiplying it by that variable T plus the startup cost of $4,000. That's the electric system. That's how much it'll cost based on the number of years that we're considering. We're going to do something similar with the heat pump system. Different startup costs, though. It's more, and a different efficiency rating. So we're going to have to use that efficiency rating to help us calculate. We'll call this C sub 2 for the second cost. So it's still 16 cents per kilowatt hour, regardless of the system that's in the home. And now we're going to multiply that by the number of kilowatt hours we need to spend per year. Except this part is a little bit different. This is how many kilowatt hours we need on the electrical system. That's how many kilowatt hours we're pulling from the electric company. Because we have a more efficient system, we can divide that by 3.5 because of our coefficient of performance. Right? So every kilowatt hour you get from the power company with this heat pump, you are dividing that kilowatt hour by 3.5 because your system has a coefficient that's bigger than 1. So for every 3.5 kilowatt hours you get 1 kilowatt. Sorry, for every 1 kilowatt hour you get from the electric company, you get 3.5 kilowatt hours of heat. So this is how much the standard electric system needed from the heating company, from the electric company, but we're going to divide that by 3.5 because the heat pump is efficient, right? Because that coefficient. And that's how many kilowatt hours we need per year. And same process. We don't know how many years it's going to be, so we're going to call that T years. And then we're going to add the $8,000 startup cost. So C sub 2 is, my handwriting is getting worse the longer the problem gets. Those cross cancel just like we wanted. The years cross cancel. So 0.16 times 26,377.49, and then I'm going to divide that 3.5. So can't see, it's a little off screen. I just took some decimals with me. I'll round to the same. Well, no, one more decimal, please. So 1 here. Okay, so that's the cost of the heat pump system. This is the cost of straight electricity. This is the cost of the heat pump system. So we will eventually, the heat pump system is going to catch up, right? It's got a lower slope, we would say, when you talk about y equals mx plus b. This number, this 1,205, that really determines how quickly the cost rises or how slowly it rises, I guess, when you compare these two. So eventually this cost will be less than this cost. But at the start, when t equals 0, the first year, this costs 8,000, this costs 4,000. So it's going to take some time to catch up. So in algebra, when you want to find out when two lines or when two equations cross each other, you set them equal to each other. So I'm going to plug this in for the cost over here to find out when the two costs are going to be equal to one another. So 4,220 point, I'll just round, well, we'll keep it. Okay, I set the two equations equal to each other. So to get t by itself, I can't solve if t is in two different places, right? T is on the left and on the right. So I can subtract 1,205.8281 t from both sides. That makes it disappear over here. So we've got 4,220.3984 subtracted by 1205.8281. So on the left side we have 3,000. I'll just copy that. 3014t. I copied the equation over here because I ran out of room. And then we're trying to get t by itself. So we got the plus 4,000 we want to get rid of. So we want to subtract 4,000 from both sides. When you do that, you're going to get 4,000 on the right side. And then the final step to get t by itself is that's 3,000 is multiplying to t. So we want to do the opposite. We want to divide both sides by 3,000. So take that 4,000, divide by 3,000, 14.5703. So I got 1.326. So it looks like within a little over a year, oops, because t is in terms of years, the heat pump system is going to be more efficient. It's going to be saving you money. That first year, the heat pump system dies, you're out of luck. And then we could verify this fact too. If you just take the 1.3268 years and plug it back into the equation, it should show you that these two are roughly equal to each other, assuming our equation's correct. You can even test it with 2. If you plug in like a year 2, how much are both of them going to cost us? So the electric system in year 2, I'm just rounding, it's going to cost us about 12,440. At year 2, the heat pump, I'll round this one as well, it's going to cost us 10,410. So a little less than a year and a half, the heat pump is starting to save us money.